going to be showing off my Minecraft computer that I recently made. It's an implementation of the LC3 computer architecture, which is a super basic educational computer architecture, so mostly used by students. However, I decided to actually make it in Minecraft. So first of all, I'm going to be going over a very general overview of all the parts of the computer. And then I'll actually be tracing through the path that data would take in the computer. Hopefully that will hit most of the major components. I can talk about them a little bit. And that's the main part of the video. At the end, I think I might go over some of the slightly more technical details, like the trade-offs I had to make, and maybe show some of the interesting Minecraft-specific components I used. But before I start, I did want to mention that I was inspired to actually make the LC3 Minecraft by this YouTube channel called Gold Fusion, who I'll link in the video description. Who also made LC3 Minecraft, so that was the reason I decided to make it. I will give a super general overview so that you understand where everything is. To start with, we'll start with this big red platform. This is our control center, you could call it. So technically not part of the computer, but below it on that white platform, we have our clock, which is the only clock in the computer and controls when everything happens. The next big part, I guess, would be this large rainbow section right here. So all the way from here, all the way down into the fog and back around. And this is our finite state machine. So this controls, you can think of it as the brain, and it basically just controls when things happen and in what order they happen. So I guess the next big section would be memory, which is all the way over here. It's this large rectangle object. And that is obviously where we store all of our data for at least a semi-long-term period of time. And then I guess connected to that would be the register file, which is that tall rectangle over there. And that is where we have 8 registers. And in each register, we can store a number that we will use to do math and logic with. So we'll take data out of memory, store it in registers, do math with it, and maybe store it back in memory or put it somewhere else in the computer. Those are the main parts. This entire left section, left of the finite state machine, is all like address-related logic. And at the very end is our program counter, which tells us which line of memory we are currently executing as an instruction. And the last part, I guess, would be this long red strip, which is our bus, which is like a two-way wire that just lets us transmit data from one component of the computer to the other. It's a shared data line. So those are all the main components of my computer. So now I'm actually going to go and show you it running. What we're going to be doing is running a super basic command. There's 15 different operations this computer can do, but one of them, and probably one of the most simple, is add. So what we're going to be doing here is we're going to be adding R5, register 5, register 6 together, and we're going to be storing that sum into R7, and I will show you that happening. So first thing we need to do, we need to insert this instruction into memory. So I've already put it out. This is hopefully our add operation, and we're going to store it into memory address 0. These are just some helpful command block tools I use to manually set memory. So at address 0, we're going to put this command. And after that, we just need to clear our program counter because we want to execute the instruction at address 0 instead of whatever it's currently at. So it should be cleared to 0 all the way over there. And then we should be able to start a computer. So we're going to start a computer. When this redstone line turns on, that means a clock signal has turned on. And I'm actually going to stop it manually. When it's on, it means that whatever our current state is has just happened, so it's finished. So that means we can go over all the way over to our memory. And now we are at our memory, and you can see how our memory address register, which stores the address and memory we want to access, is all zeros. So each of these bits in binary are zeros. And importantly, our next memory address we're going to access would be 1 if we use the program counter. So the program counter is now at 1 because our next instruction that we will run is going to be at address 1. We obviously don't have one. We're only running one instruction, but if we did have more than one, then that would still work. And we should see There we go. So it's now finished. Memory address is at 0, and we can see what is in memory address 0. Well, it's our command 0, 1, 1, 0, 0, 0, and so on. Each of these repeaters are a bit of memory. So you can see this one's on, that's a 1, a 1, a 0. And this is the first row, which is the first memory address. So there's 8 in each column, and then there's 8 modules of these. That's 64 memory addresses. If we turn on the computer again, we will see this come into the memory data register. And you can see that now, after the clock cycle is finished, our instruction, I guess you'll have to believe me, but this is the add instruction that we just had in the 0th position in our memory. So after this, it's going to go along the bus here, and it'll go all the way over to our instruction register. The same exact memory address will go into here. And you can see how it just switched. Now our address is in our instruction register. So this is the register that stores our current instruction that we're about to run. So we just ran through what's called the 3 stages of fetch. We just finished fetch 3, and we're about to move into our decode state. Our decode state does absolutely nothing in my computer, but it is a part of the LC3. We're at our state machine. This is our actual state. This is the register that controls our state. We have 6 state bits, and this is our current 6 bits, and these are our next state 6 bits. And you can see right now, this corresponds to a state of fetch 3. And after this redstone wire turns on from the clock, we will transition into decode. So you can see that now we're in decode. It just switched states, and you can see the next state is add. Only the first bit's a 1. And so now we have just executed decode, which does nothing, as I said. And then we are about to go into add state right after this. Now we're in the add state, as you can see. Only this bit is a 1. After we're done with add, we are done with our instruction. So our next one is to fetch 1, the first stage of fetch, where we'll fetch our next instruction, which doesn't exist because we're only running a program with 1 instruction. While we're looking at our finite state machine, we can look at exactly how the state machine affects the rest of our computer. So given that we're in the add state, it will turn on, first of all, the next 6 bits. And this is just a bunch of and OR gates all hooked up together. And then after the next 6 bits, we have all of our control signals, which basically each go to one component. Some components have a couple that go to them, and determine for registers, like whether they should be written to. For like our arithmetic and logic unit, it determines which operation we're doing. And so on. So you can see how these are all off, and then this one is actually on. So what's this? Load register, right? Because we just finished adding, and in the add state, we want to load R7, which is a register. So we have to load register. Now that we're in the fetch state, because this bit's a 1, I can go and show you our register file, and we can see all the values of R5, R6, R7, and then we can see what happens after this state finishes. So we are at our register file, and R7 will be the top register, it's the last register. And you can see I've completely cleared it before the video, so it's all zeros. And this one is not all zeros, these 2 bits are 1s, so it goes 0, 1, 1. And this is the value 6, if I'm correct. So R6 is currently 6. R5 is currently 15, I believe. So what we'll be doing, remember, is adding R5 plus R6, and then storing it in R7. So we're going to add 15 plus 6, which I believe should equal 21, and that should be the value in here when our instruction is done. Now, we're actually in the add state right now, so we can see what will happen at the end of the state. So you can see how these are outputs of our register file. So it's reading from R5 and R6. One of these, I forget which, is R5 and one's R6. This would be R5, right? And this is R6 because that's 6 and that's 15. And we're going to add these two together. So we go all the way over here. We're just following the line like the data would. And we come into our arithmetic and logic unit that I talked about in the beginning. Or I may not have, but this is our arithmetic and logic unit. And you can see how we are just adding our two numbers together. The arithmetic and logic unit can also do bitwise and bitwise not. But we are using it for add rather, because that is the instruction we're running. So you can see that the output of this ALU on the other side, that the bits here at the output go 1, 0, 1, 0, 1, which is 1, plus 4, which is 5, plus 16, which would be 21. And that is our correct answer. So, continuing along the path, we go back onto the bus, and we actually go over here. We're still on the bus, technically. Well, actually, this is like an extension off of the bus. And this goes into the input of our register file. So you can see how we want to store this in R7, and we have the first bit is 1, 0, 1, 0, 1. Once this redstone line is triggered, we will write to this register, and we should get our expected value. How do we know which register we want to write to? Because we only want to write to R7. Well, we have these selector bits here, our address bits. So 111 would be 7 in decimal, if this is in binary. And then this is our actual clock signal. So this will turn on when we actually want it to happen. This is just deciding which row of these we want to actually change. And so we can see that happening. So you can see how it just changed. We have 10101, which as I said is 21, which is the sum of R5 and R6, and we put it in R7. So you can see how we've executed a basic add operation pretty slowly, but we did execute it. And I was stopping it in between so we could get from place to place. But that is about it. I mean, the process for the other operations are the same. The other 14 operations. Minus a few because I didn't implement them. Just different sections of the computer, but almost always involving this register, sometimes involving memory. Actually, always involving memory when we want to fetch the instruction out. And that's pretty much it. If I forgot to mention, the clock cycle is 28 seconds per clock cycle, which is quite a long time. But we ran our instruction. Our next stage will be to fetch a new instruction, which we're not going to do because we only actually inputted one. The last thing I wanted to show you is that I did run a more complex program on here, which is to find the first few elements of the Fibonacci sequence. I don't want to show it because it takes hours to run, but I did run it, and we can see the results in our memory if we go over there. So I'm now at our memory, and my Fibonacci program took up these two columns almost fully, just to put the actual code in, the assembly code. So this is the first slot that was open to actually put our Fibonacci numbers. So this number is a 1. You can see all the other ones are off. And after 0 and 1, which I defined as the first two numbers of the Fibonacci sequence, 1 is the next one. So that's correct. Now going to our next memory address. Down here, you can see we have a 2, right? And so 0, 1, 1, 2. And then we have a 3, which is correct. And then we have a 5, an 8, a 13, and a 21, which actually happens to be the same number that we put into our register, just by chance. And this is just a garbage value. I stopped running it here because it had been running for long enough. And then for some of the Minecraft specific components in my computer. This is a D flip-flop, which is very important for my computer because every single bit of every register is made up of this. So this is 1 bit of memory. So that includes my memory, my register file, my program counter, my condition code register, my instruction register. Every single register is made up of this kind of memory. And you can see how it works. It's super small, which is nice, benefit of Minecraft. being able to lock repeaters. If a repeater is powered through the side by another repeater, it locks it, which is kind of interesting. And so this is our input. If we turn our input on and then we give it a clock signal, then it changes, it remembers our input at that time. So we can turn this off and it doesn't matter because our clock signal isn't hitting it. But if we turn another clock signal, then it'll turn it off, right? And then it'll only happen on the rising edge of this clock signal. So this is a super nice, compact D flip-flop design. And then the second interesting Minecraft component are these instant redstone repeaters. I use these anywhere where you would have to extend the redstone signal with a normal repeater, which introduces 1 ticket delay. So I did not invent these, I found them off the internet, but they do work and transmit a signal as if there's no repeater here. So I use that all over to kind of negate the fact that my computer is so spread out. The distance doesn't matter as much, other than lag. I'm now down at our bus, and remember this is the two-way wire that connects all of our components together. And so I also wanted this to be instant. Actually, this is probably one of the most important parts to be instant. But those repeaters are one-way. So I had to find a two-way design, which is a bit wider, but I think it's a pretty simple design. It takes about 1, 2, 3, 4 blocks wide each, which is not horrible. But this transmits the signal both ways. So the signal is coming from somewhere over there, and it's being transmitted all the way over there. But if we had a signal from there, it would also go to there. And that's about it for the most part for our computer. So hopefully you enjoyed taking a look around the computer. The download for this map will be in the description. It's a 1.16 map, but all the components used here are not 1.16 specific. I actually made it in 1.12.